Hello and welcome to today's lecture. So, in the last lecture we had a brief recap of R and how you can enter vectors in R and do basic calculations or basic operations with vectors, and also we saw how you can use R to calculate descriptive metrics including mean, median, standard deviation, so on and so forth. Okay. Towards the end of last lecture we started discussing about bivariate data and how you can say something about correlation between two different variables, right. So, let us take a look at what we mean by bivariate data. Let us say we have two variables x and y, and we can have various values, let us say 1, 2, 3, 4, 5, 10, 9, 8, 7, 6. Let us say this is one example of an x and y. So, if we plot this data in the x and y plot, so what I have is something which, so this is 1 and 10, 2 and 9. Okay. So, you have these 5 points. Okay, let me make the points darker. So, these 5 points, right. So, you get the feeling that there exists an correlation or an inverse correlation, that is with increase in x there is a decrease in y. And how do you, and let us just say, so this is a very good data, you can clearly see that there is a clear line which passes through all these points. But in the more generic case, let us say you have points okay, this is more likely to be a data. Now, in this case what kind of a line will you draw? Will you draw a line which is like this, will you draw a line which is like this, or will you draw a line which is like this? Okay. So, in order to go ahead with these kind of thought processes, what we do is we find out something called correlation coefficient, and then based on that we go ahead to a concept called regression. Okay. So, let us revisit what we did about correlation coefficients. So, we define the correlation coefficient rho or R, okay, and this is given by the expression is equal to Sxy by Sx times Sy. So, Sxy refers to the covariance of x and y. Okay. So, if you see the symmetry, so if you have Sx, so we know, so we have R or rho defined as Sxy by Sx comma Sy, Sx product Sy. Now, rho is a measure of correlation, right. So, what should ideally be the values of rho? You can say something as highly correlated, or uncorrelated, or weakly correlated, uncorrelated or weakly correlated. Okay. And within high correlated you can have positive correlation or negative correlation. So, in the example we showed in the first slide, so this is an example, the original data set is an example of negative correlation where increase in x leads to decrease in y. So, if we see the way rho is defined as Sxy by Sx by Sy. Okay. So, ideally we should have, when it is highly correlated, we should give a value which is positive. So, highly positively correlated should give me a value which is closer to +1, negative correlation should give me a value which is closer to -1, and uncorrelated should give me a value approximately equal to 0. Okay. So, if we see our definition of rho and ask how do we define the covariance. So, covariance is defined as, so Sxy is defined as summation of x minus x bar times y minus y bar whole divided by n minus 1. Okay. So, what you clearly see missing is the square root. So, if I write down the corresponding expression of Sx, I have square root of x minus x bar square whole square by n minus 1. Okay. So, in the definition of covariance this square root is missing, and the reason is obvious. So, you are multiplying Sx by Sy which has square root, okay, y minus y bar whole square by n minus 1. Okay. So, if x has units of meters, let us say, then and y has units of meters, let us say. So, then x y, so this will give me a value of meters, this will also give me a value of meters, and this the top portion should I also give me a value of meter square. So, that s x y by s x x y, so s x y by s x times s y should be non dimensional. Okay. And this is why you have this, the root does not exist in s x y. So, it is possible we can simplify s x y. Okay, we can simplify s x y by writing summation of x minus x bar into y minus y bar by n minus 1. So, I can simplify this to summation of x y minus x y bar minus x bar y plus x bar y bar whole by n minus 1. Summation x y minus I can take y bar out, summation x minus I can take x bar out, summation y plus x bar y bar summation 1 whole by n minus 1. Okay. So, this I can write as summation x y. So, y bar is okay. So, I can have y bar and summation x is to n into x bar, similarly x bar into n y bar plus x bar y bar into n by n minus 1. Okay. So, this and this cancel out, and what you are left with is the expression s x y is equal to summation of x y minus n x bar y bar by n minus 1. So, I can rewrite this equation as okay. So, summation x y minus summation x summation y by n whole divided by n minus 1. So, this is a simplified expression for calculating s x y. Of course, when you are doing these calculations in a laptop or in a program, then you can use the original formula to calculate the final expression, but when you are doing it by hand, then this is the easier way to calculate. So, let us take one sample example and work it out to find out what is the expression for s x y. Okay. So, let us take x and y. Okay. So, let us say so you have the following values of x and y. So, okay, so let me remove the last one. Okay. For simplicity, let me remove the last value. You have 5 values of x and 5 values of y. Okay. So, I want to calculate the value of s x y, and I want to calculate the value of correlation coefficient. So, first before doing the calculation, let us see how the values look. Okay. So, 5, 4, 3, 2 and then 2. So, you have these points which are coming down, but then there is a flattening beyond this point. So, had I plotted 6 and 2, then it would have also lied somewhere here. Okay. So, let us see. So, what I can clearly see is towards the initial part there is a very clear negative correlation, and towards the latter side it is kind of flattish. Okay. So, let us calculate the exact expression for s x y. I will again write down the values of x 1, 2, 3, 4, 5, x is y is 5, 4, 3, 2, 2. I can write x y, I can write x square and y square. Okay. I can calculate these values 9, 8, 10, 1, 4, 9, 16, 25, 25, 16, 9, 4, 4. Okay. So, so summation of x y is equal to 27 plus 13, 40. Summation of x square equal to 25, 26, 40 and 13, 53. Summation of y square equal to 9 and 8, 17 and 33, 58. Okay. Summation of x, of course, y is equal to 16. Okay. So, my s x y is given by summation x y, which is equal to 40, minus summation x is 15 into summation y 16 by n, which is 5, whole divided by 4. Okay. So you see a value. So, this I can simplify. 15 square is 225, 240 by 20, 40 minus 2. So, s x y is giving me a value of minus 2. I can go on to calculate the value of s x. S x is equal to square root of summation of x minus x bar whole square by n minus 1 is equal to root of. So, in this case x bar. So, x bar is equal to 3. So, it is 2 square plus 1 square plus 0 square plus 1 square plus 2 square, whole divided n minus 1 is 4 is equal to square root of 4 plus 4 are 10 by 4 equal to root of 2.5. Okay. I can calculate the value of s y is equal to root of y minus y bar whole square by n minus 1, y bar is equal to 5 plus 2, 16 by 5 equal to 3.2. So, s y, okay, 1.8 whole square. Let us take a different pen. 1 plus 8 whole square plus 0.8 whole square, okay, 3.2 whole square plus 2, 1.2 whole square plus 1.2 whole square, whole divided by 4, roughly 3.24. So, I can calculate this as, so 2.44 is 2.88 plus 0.04, 0.64, 1.8, 3.24, 0.324, sorry, 3.24, 6.8. So, root of 6.8 by 4 is square root of 1.7. Okay. So, I can write s x y is equal to minus 2, s x equal to square root of 10 by 4, s y equal to square root of 6.8 by 4. So, my rho is equal to minus 2 by square root of 10 into 6.8 by 4 into 4, which is, okay, minus 2 into, I can have the 4 out, by root of 70, okay, equal to minus 8 by root 70, okay, which gives me a slightly negative value, which is, so this I can approximate as 8.5, let us say. So, I have the correlation, it has to be greater than 8.75. Okay. I will get a value rho which is almost close to minus 1. Okay. And this is obvious from the data, because the data looked something like, okay. But what you also, this is my x axis, this is my y axis. Okay. So, what you clearly see is this correlation coefficient is negative, that means that as you increase x, y decreases. Now, based on this, can I come up with a way to predict that given a value of x, what will be the value of y? And that is what we do using regression analysis. Okay. So, in regression, okay, what you do is, let us say you have a set of data points x and y. Okay. Imagine these are your data points, and you want to be able to predict such that given x predict y. Okay. Now, if let us say one way, the way I have drawn this data, I can see that if I draw a line which is roughly like this, then this might be a good way of predicting the value of y, and I have intentionally drawn a line which somehow crosses through the middle of all these points. Okay. I could have also drawn the points like this, but in this case what you can clearly see, while this line will predict y quite well in this regime of x, but in this regime of x there will be a huge disparity. Okay. So, what is the method to madness? What is done in linear regression is what you try to minimize. So, if you have x, you have y, and you have these points, okay, you draw a line such that the errors which accumulate for each of these points away from this line. So, for each point you can calculate how far is the estimate from the actual value. So, these are your actual values. Okay. So, these are your actual values, and these are, this is the predicted line, right. So, what you want to know is, can I draw a line such that the sum of these numbers or these errors which accumulate from the prediction is minimized, and that is what is called in what is done in linear regression. Okay. So, let me reframe the problem statement. Okay. Let me reframe the problem statement. So, you have, let us say x1 y1, x2 y2, x3 y3, n values, let us say. So, you have xn yn. Okay. Given n values, can you draw a line y is given by a plus bx. Okay. So, these are my x and y values, and my predicted values. So, if I were to draw this particular line as the estimate of the values, I can write that at this particular value it is a plus bx1, a plus bx2, a plus bxn. Okay. So, what is the error that I accumulate from my prediction? y1 minus a plus bx1, y2 minus a plus bx2, yn minus a plus bxn. Okay. Now, let us say if I say that I want to, so my total error is what I want to minimize. This has to be minimized. Okay. So, now if I were to define error as just summation of yi minus a plus bxi, okay, would this be a good metric? And the answer to that is no, because given your points, so given your points, okay, if given your points and you were to draw this particular line, okay, so you can clearly see that in some cases this error will be positive, in some other cases, so this is negative, this is positive. Sorry, the other way around, this is positive, this is no, this is negative, this is positive. So, some errors will be positive and some errors will be negative. So, this function error is equal to summation of yi minus a plus bxi. If you actually do it, you might get a value of error which is close to 0, but this is not what we are minimizing. We are minimizing the sum of these, each of these deviations from the actual value. Okay. So, what we need to minimize is this particular function error given by So, I take the square, so which means that what I count, both whether it is positive or negative, when I take the square, it is something which contributes to the error. Okay. So, I want to minimize this function. How do I go about minimizing this function? Okay. So, there and you want to go at the end of the exercise, what you want to do is to determine values of A and B such that error is minimum. Okay. So, this is what you want to minimize the error. Okay. How do you do it? So, if you recollect, so in class 12 standard calculus, what you did was, if you had a function f of x, right, in order to minimize, okay, in order to minimize, you set f prime of x is equal to 0. Okay. So, let us take a sample example. Let us say f of x is equal to x minus 1 into x minus 2. Okay. What is the value of f prime x? Is equal to x minus 2 plus x minus 1 is equal to 2x minus 3. Okay. If I said f prime of x is equal to 0, then I get x is equal to 3 by 2. Okay. Now, if I actually plot this whole function, this is x, this is y, let us say this is 1 and this is 2. At x equal to 1, the function is 0. At x equal to 2, so let us say this is my value x, this is my value 2. At x equal to 0, if I put x equal to 0, then it is minus 1 into minus 2, which is something which is positive. Okay. At x is equal to 3, for example, again it is positive. So, this tells me that the function will look something like, so it is nothing but a parabola. Okay. So, with the minimum, this is where I am calculating the minimum. So, f prime x equal to 0 means x is equal to 3 by 2. So, this is x equal to 3 by 2 point. Okay. But let us say, so in our case we want to minimize this particular function. So, in our case we want to minimize this particular error, okay, is equal to summation so my error is actually a function of a comma b. So, if you have more than one variables, then the way you minimize is by, instead of taking a regular differential, so let us say E is equal to error, which is function of a comma b. So, what I write down two equations, del E of del A is equal to 0 and del E of del B is equal to 0. Okay. So, these are called partial derivatives. Okay, these are called partial derivatives. So, let us say for example, if f of x y is equal to x y, let us say plus y square. So, del f del x is derivative with respect to x assuming y is constant. So, my del f del x will return me a value of y. My del f del y will return me a value of x plus 2y. Okay. So, if this is how, so when you take the derivative, partial derivative with respect to x, you assume that y is constant. So, of course, so if y was a constant, when you take this derivative, it is simply y, and because y square is treated as a constant, del f del x or del x of y square is equal to 0. So, this is actually y plus 0 is equal to y. Okay. Similarly, I can take del f del y is equal to x plus 2y is what I get. Okay. So, now coming back to the problem, okay, I have two equations. My error is equal to f of a comma b, okay. So, let me find out the partial derivative with respect to a. Okay. So, you can, let us say if I were to say z is equal to yi minus a plus bxi. Okay. So, I can write this as is equal to summation of, okay, so okay, if I do this particular z, then I can take the derivative. So, my error is of the form summation of z I square, z square. Okay. So, I can write down my del E del z. So, this is nothing but it is nothing of the form. So, del E del z is of the form summation 2 z. Okay. So, and del z del A. So, del z del A is of the form minus 1, because you treat everything else as constant and you take the partial derivative with respect to A. So, my del E del A will give me an expression of twice summation of yi minus A plus bxi into minus 1, and this is equal to 0. Okay. So, I have del E del A is equal to 2 summation of yi minus A plus bxi whole into minus 1 equal to 0, which I can simplify, would simply imply summation of yi minus A plus bxi is equal to 0. Okay. So, this implies summation yi is equal to summation A plus summation bxi. So, I can, so this n times A plus b summation xi. Okay. So, this is nothing but n times y bar. I can write n A plus b times n times x bar. So, this would give me the expression y bar is equal to A plus b x bar. Okay. So, what we have determined, so two things we have discussed. We have worked out the case of correlation and shown how to calculate the correlation coefficient, and then we wanted to go to the next step, where we wanted to show, can you find out a line which can be used to predict the value of y given a value of x. And as part of that, what we use basics of calculus and partial derivatives. So, we determine an error function, and we say that we want to minimize the sum of all the deviations of the values of yi from what is predicted from that line, and this is what we want to minimize, and this is the first equation that we minimize when we write del E del A equal to 0. So, with that I will stop here. I will continue in next lecture, where we derive the next equation for regression and see how regression can be made use of to predict a line and predict a value of y based on the line estimate. Thank you for your attention.